Okay, so again, let's think about some more examples of confounding and common response. So here's a new example. There was an article that appeared in the the Journal of the American Medical Association back in early 2000s, 2004, and it was looking at at a link between taking antibiotics and developing breast cancer. So as you're reading here, researchers found that women who took the most antibiotics have double the risk of developing breast cancer compared to women who didn't use the drugs. So does that mean that I cannot talk today. Antibiotic use causes breast cancer. Okay, so what could be going on? So certainly there could be a causal link here. So it could be that if you take antibiotics, that's going to cause breast cancer or some kind of cancer. But again, this was not an experiment. So researchers were just noticing that there was this link between women who were taking antibiotic for whatever reason and who seemed to develop a certain kind of cancer. So we'd want to be careful not to jump to the conclusion that one is causing the other. Why? So it could be that we have confounding going on. So what would confounding look like? So remember, confounding would be where we have our response, we have our explanatory variable, there's a link between the two, but there are all these other things going on that we have not taken into account. So what are all the other things that could also affect developing cancer? Well, maybe having a poor immune system, the environment you're in, the diet you're eating, whether you're a smoker or not, the amount of stress you're under, genetics. We could come up with probably a much longer list here. But what's important to note is that you have all of these other things going on. They're all getting mixed up together because we haven't controlled for any of these other things. So we can't really know, is it the antibiotic use that's leading to the cancer? Is it one of these other things? Is it a combination of all these things? So this would be what confounding looks like. Now, common response would be where perhaps if you have a poor immune system, maybe you need to take more antibiotics or a different kind of antibiotics. Maybe having a poor immune system somehow affects whether you're taking antibiotics. And maybe having a poor immune system makes you more susceptible to developing cancer as well. And because of the fact that this third variable is related to both of these other variables, it's making them look like they're related to each other when perhaps they're not related to each other at all. So if we didn't have this, if we could control for that in some way, maybe antibiotic use really isn't related at all to cancer. So this would be what common response is. So again, both common response and confounding deal with a third lurking variable or more lurking variables coming into play, but how that variable is coming into play is a little bit different. Now, one thing that chapter 15 does a nice job of explaining kind of toward the end of the chapter is that, certainly there are times when we might be interested in relationships between variables, but it's just impossible ethically for us to be able to conduct an experiment. One big example of this is the link between smoking and cancer. So you might feel that smoking is not good, it's going to lead to a certain kind of cancer, but obviously it would be very hard to conduct an experiment. Ethically, it would not be possible to conduct an experiment with humans where you know something is bad and you're forcing them to do this to see what's going to happen down the road if they're going to die from a disease of some kind. So in some cases, we really can only rely on correlation research to be able to talk about links between variables. But it is possible in some cases to make a strong argument for causation, even if you haven't been able to conduct an experiment. But to be able to do this, a lot of things need to line up. A lot of things need to be happening at the same time. So you need to make sure that there's a strong association between your variables, for one thing. So again, you plot things, you look at your scatter plot, you look at the correlation between the variables. You want that relationship to be consistent in different situations. You want higher doses of one variable to be associated with stronger responses. The cause should naturally come before the effect. the cause is plausible. So again, all of these things would need to line up. You'd need to make sure you had all of these things before you make a good case that these variables are associated with each other. So it's very likely that this one variable is causing the other. But again, even if all of these things are going on, it can still be really, really hard to say for certain that one variable is causing another. Because again, there's just always the possibility that there's something that you haven't controlled for, that you just haven't thought about, or you don't know about, that is affecting that relationship. So again, a big thing that we want you to remember from these chapters is that we can talk about associations, we can describe associations, but we don't want to jump to the conclusion that one variable causes another. And I have kind of a link down here. Unfortunately, this documentary, I don't think it's available anymore, but a few years ago there was an interesting documentary on PBS about cancer. And I just have a link here in case you're interested in this kind of stuff. And it might be floating around on YouTube or somewhere on the web if you really want to look at it. Or maybe one day it'll come back on PBS as a rerun. But it was really interesting because there were several different episodes of this documentary. And in one particular episode, they were talking about this link between lung cancer and smoking. And they were looking at how things seemed to spike in terms of the incidences of lung cancer when there were lots of advertisements about cigarettes. And so it's really interesting because a lot of these things that are coming up in chapter 15 were discussed in that documentary. So I hope one day it'll be back on because, again, to me, it was very interesting anyway. One thing we always have to think about is it's possible that sometimes there's just a coincidence, that a couple of things are related to each other and we're trying to rack our brains thinking about, well, what could the possible lurking variables be? But it could just be a coincidence. And there's a nice website, I have a link to it down below here, that kind of shows a lot of these spurious correlations where there are two things that are related to each other, but it's really probably just a coincidence. So this was kind of a funny one. The per capita consumption of cheese in the United States and the number of people who died by becoming tangled in their bed sheets. So we were looking at lots of different years here. The correlation is pretty strong. Probably just a coincidence. I don't know though. Maybe the more cheese you eat, the harder it is to maneuver yourself in bed and the more likely it is to get tangled up. I don't know, but probably just a coincidence. Here's another kind of funny one. If you're a Nicolas Cage fan, you might like this one. So the number of people who drowned by falling into a pool and the films that Nicolas Cage appeared in. So for several years, those variables were looked at. Here the correlation isn't as strong as before. It's 0.66, 0.67. But, probably just a coincidence. I don't know if people are drowning because of not liking these films, or I don't know. I'm not gonna make any bad judgments about Nicolas Cage, but probably just a coincidence. So again, if you go to this website, there are a lot of other fun things that you can look at. So we're getting to the end here. I know you thought it would never come. There's just one more thing I wanted you to think about, which I thought was kind of a nice way to wrap up everything that we've talked about here. So well, I want you to imagine 4 data sets. So each data set has an X and a Y variable. We want to see if X and Y are related within each data set. Each data set has the same number of observations. And it turns out that with each data set, the correlation between X and Y is exactly the same. The regression equation is exactly the same. And I noticed I should have put a little hat here. So predicted Y equals 3 plus 0.5X. So think about that. And I want you to think about what we don't really know. So we're given a good amount of information here. There are a few things we don't know. And there's one big thing that we should know before we can make sense of this that we would want to make sure is going on. So I want you to think about what you think it is. I presented this one time in my face-to-face lecture, and one student said, well, we don't really know what X and Y are, so that's certainly something we don't know. We don't know the exact sample size. So knowing those things, of course, would be useful and would help us make more sense of this. But the one big thing I wanted you to be thinking about is that we always assume we always start by assuming that we have a linear relationship between x and y. And here we don't know that. You might be thinking, well, we probably wouldn't want to compute r and figure out the regression equation if we didn't have a linear relationship. But mathematically, you can still figure these things out, even if the relationship is not linear. You wouldn't want to interpret these things in a statistical context, though, if you don't have a linear relationship. And so it turns out, if you look at all four of these different data sets, some interesting things happen. So here's what the data sets look like. So obviously here is kind of what we would want. That's the ideal. But notice the lines in all the plots, that's, if we use that regression equation to make some predictions, that's what the line would end up being. But notice that the line is really not fitting the points in all of these different plots. So here the line is a good representation of those points. It's fitting the data. Here the line is not fitting the data because we have a curved relationship. So we wouldn't want to use this line to make any predictions because the relationship is not linear. Over here as well, it's not really a linear relationship. X and Y, or X can only take on two particular values here. So we really wouldn't want to use this equation to make predictions. Over here, we could maybe use the equation, but we have to think about the fact that we have this unusual value and think about how that's affecting the regression line. Think about how it's affecting the correlation. So the correlation was fairly strong without the outlier, or with the outlier included, but if you removed that, the correlation would be even stronger. So we'd be doing a better job predicting if we didn't have that value. And we have to think about how that value is affecting R and what the regression equation is. So if we suddenly decide we don't want that value, we're going to remove it, we would have to redo our analysis and come up with a new equation and then use that equation accordingly. So I just thought this would be a good place to stop things, and hopefully I've given you a lot to think about here with chapters 14 and 15. Again, please be sure to read through the corresponding content in the book if you haven't already, just to hear another way of talking about things and to see a few other examples. So I will see you again soon in our next set of videos. Thanks, everyone.